Are there any public comments? We'll go right into item number 1, presentation on the BPUB Water and Wastewater Master Plan.
Good afternoon, Madam Chair and committee member. My name is Marie Leal, and I am the Director of Water Wastewater Engineering and Capital Planning. The purpose of the master plan is to study and develop a plan giving comprehensive guidance and long-term strategy for improving the BPUB's water and wastewater infrastructure, and to also investigate the projected system demands. This plan will develop a CIP for the water and wastewater systems with also projected loads based on the land use assumption plan prepared by the City of Brownsville. Today, we have Ethan Shires with Breeze Nichols, who will present the findings of the Brownsville Public Utilities Board Water and Wastewater Master Plan.
Oh, thank you for your time. You guys hear me okay? If I can see it here. So yeah, thank you, Marie, for that introduction. Like you said, yeah, we're here to talk today about the Brownsville PUB Water Wastewater Master Plan. We're right here at the tail end of the project. We've got everything just about wrapped up and wanted to present the findings to you guys and ultimately our recommendations and future capital improvement plan and budget numbers. So
just sorry to interrupt.
Yeah, you okay.
But even though we can hear you, we normally ask people to speak into the mic for the audience. So if you can.
Is that better?
Yeah.
There we go. Okay. Yep. And I can use these microphones, so I appreciate that. And if you have questions, kind of throughout the presentation, feel free to just interrupt. I appreciate that. Yeah, as I was saying, we're here to kind of present the findings and recommendations from the Water Wastewater Master Plan. We'll kind of start with the background information and what we use to develop our hydraulic models, everything that went into this study. We'll talk a little bit about the growth projections and what we're anticipating out into the future to roughly 2050. And then we'll start talking about system analysis and CIP for both systems. Have some time for questions there at the end. So to start, just kind of an overview of the BPUB's water and wastewater system. So starting with the water system. It's a fairly simple system. You know, we're fairly flat down here in the valley, right? So usually elevation change is what causes us issues on a water system. We don't have too many issues there. So we just have the one pressure plane. We've got 3 elevated storage tanks totaling 6 million gallons of elevated storage. We also have 3 water treatment plants. They give us a total production capacity of about 50 MGD, that's million gallons per day. But from a pumping capacity, we've got even more than that to meet demands up to 85 MGD. And so you kind of see a map of the system there in the background. We've got a kind of schematic there shown as well. And so kind of the first task with this project is really trying to understand, okay, how do our distribution system and collection system on the wastewater side, how do they work? What are the major facilities that are involved? What are our capacities? What are the transmission lines? That kind of thing. So that's kind of what we're showing there. Then we go through and we do field data collection. And so for the water system, we went out and installed 20 temporary pressure recorders. We also pulled available SCADA information from all the facilities, tanks, pump stations, treatment plants, and got historical production information for the last decade through almost all the way back to 2010. Trying to get an idea, okay, how does the system operate? How do the pressures change? How do demands change over time? How has the system kind of changed from a production and consumption standpoint over time? And so we use all that information to develop a hydraulic model. The industry buzzword is digital twin, but ultimately what we're trying to do is we're just trying to replicate the existing distribution system on our computers where we can kind of stress test it, figure out, okay, where are the weak points, where are the strong points, where do we have capacity, where do we need to kind of construct some additional capacity. So with all that data we collected, we then calibrate the hydraulic model. And you can kind of see that second graph there on the top right is an example of one of our calibrations where we take that observed data for a representative day, typically in the summer when demands are high. High demands typically correlate to low pressures. And so that's kind of where we're stressing that system. And then we run our simulations in the model and try to match those observed conditions and kind of see how those lines match there. So in general, we feel like, have a pretty good understanding of how the water system operates, and we're able to get our hydraulic model to really well match the conditions of the existing water distribution system. So any questions on water before we jump to wastewater? So wastewater system, same process, right? Unfortunately, where, flat, lack of elevation kind of benefits us on the water side, can really cause some challenges on the wastewater side. Typical wastewater systems are operated by gravity predominantly.
I do have a question.
Yes, ma'am.
So based on these models, can you tell where the, like water is being wasted, like leaked?
So yeah, we haven't conducted what's called a water loss audit. But what I can tell you is from, like I said, we went and evaluated about 10 years worth of historical production data and consumption data. And those are just over that time period are fairly in line. So typical rule of thumb is about 10% water loss is kind of average system wide. And you guys are well within that range. So I can't kind of narrow that down any further. But I can say that I don't really think water loss is a big, major issue for the system.
I'm just wondering what this modeling can tell us.
Mhm.
I mean, so I see a
Yeah,
map,
sure.
so I'm assuming that you're able to tell like water going to different parts of the city.
Right.
All right.
Yeah, so primarily what we're using these models to evaluate is the capacity of the system, and how that correlates most directly is pressure. So you turn your faucet on, you're in the shower, right? What's the pressure behind that water? How fast is it coming out? So TCEQ regulates the minimum pressure in a water distribution system to 35 PSI. And so that's kind of our primary checkpoint. There's some other things I'll get to here in a second in terms of exactly what we're checking for. But ultimately, that's what we're using the system to evaluate is how are the pressures kind of throughout the system.
Okay.
Answer your question?
So not geographic.
No, and it is spatial, yeah. So I've got some maps and, we kind of got pretty slides here with some things hiding. But yeah, I'll show some graphs or some maps here in a few minutes that show kind of that pressure distribution. We also look at available fire flow, which is kind of system capacity from a flow standpoint. So yeah, absolutely. It's definitely we look, part of what's important about this calibration, you can see that graph, those graphs there are the fluctuations in pressure over time. So obviously, when everybody wakes up in the morning, starts using water, showers, whatever, that increases your overall consumption. That's typically kind of when those pressures kind of drop. And the night when everybody's sleeping, nobody's using water, the system can kind of recover, fill the tanks and that kind of thing. So we want that, what we call temporal analysis, but then we also look at the spatial analysis as well to say, okay, obviously right next to your ESTs, your elevated storage tanks, right next to your plants, you have really good pressure, you have really good system capacity. What about on the far outskirts of the system? Are we still able to maintain that pressure kind of throughout the distribution system?
Okay, thank you.
Think so? It was a great question. Thank you. So yeah, kind of similar on the wastewater side, right? So like I was saying, where the elevation kind of benefits us here down in the valley, it kind of, bends back and bites us a little bit on the wastewater side. Because it's so flat, wastewater systems are typically gravity driven. So, when you use your water, it goes down your sink, what have you, they flow through gravity in the same way a river would flow, kind of to the ocean. There are wastewater gravity mains, they're flowing to our treatment plant. Unfortunately, when it's really flat, you got to dig those pipes really, really deep to maintain that gravity fall kind of throughout the system. And we utilize what's called lift stations to boost that flow back up. It gets kind of exponentially more expensive to continue digging lines, especially around that like 20 to 30 foot range is about as deep as we can go. So the BPUB wastewater system has 177 total lift stations. Don't quote me on this, but to my understanding, based on kind of work experience around the state, I believe you guys are second only to the city of Houston in terms of total lift stations on your wastewater system. Yeah. It's a very, very complex system. And I think that's really important kind of context to provide. Talk about the water system, relatively simple. Well, the wastewater system is fairly complex and especially kind of, related to your peer utilities in the area. And that's going to kind of come out on how do we have to maintain those systems. That extra complexity, makes it hard. It makes it difficult. It's a challenge that you guys are faced with to maintain that level of service that you have today.
So question,
Yes, ma'am.
is it that we have so many because of the terrain, or is it because of our sprawl?
The sprawl, is that what you said?
Yeah.
Yeah. It's a little bit of both. Typical process is as you kind of grow, right? It starts with the city center and then you go out in the suburbs and kind of, and I always like to say, the easiest place from a utility standpoint to serve is always right next to your treatment plants. So if anybody's looking, for a house, from my opinion, you want to put it right next to your treatment plant. Obviously, there's other reasons why you wouldn't want to do that. That's never how it happens, right? So obviously, all that new growth is kind of occurring on those outskirts, and it takes a lot of infrastructure to get the water out to those developments. And then when it generates wastewater, enters back into the wastewater system, we got to get it back to the treatment plant. So that's definitely part of the problem. But ultimately, what y'all, the challenge that y'all are faced with here is just topography. It's just that simple that it's really flat down here in the valley or kind of on the coast. And so we see other cities like Corpus Christi, like I said, Houston, when you have that kind of flat terrain, that correlates to a, high level of lift stations, especially density wise.
Yeah, for people that live kind of in the outskirts, just because I grew up in the outskirts of Brownsville, we had septic tanks, right?
Right, absolutely.
We manage it there. We don't connect to the system. We have our own standalone.
And there's definitely some of those, the BPUB will provide water service to some areas that they don't provide wastewater. So we'll get to that here in a second about kind of the differences between the service areas. So yeah, that's definitely part of it. And it's, as we talk about development, that's I can tell you some of the calculations that developers are doing. Okay, what does it look like to kind of get service out here? So it's all kind of part of this thing. And I think it's important context too, that, right now we're talking about how do we understand the existing system. What we're moving towards is trying to project out into the future. Ultimately, all we're trying to do is a budget tool to help you guys manage your system through the future. So we, polish our crystal ball. We think it's well calibrated. We come up with as best we can, but obviously, we're still trying to predict the future. And so kind of putting appropriate context there, factors of safety, conservatism, that kind of thing as well is really important. Okay. We'll keep going. So yeah, really complex wastewater system. And so again, on the same kind of task that we were faced with is trying to get wrap our heads around, okay, how does the system operate? Where do we have capacity? Where do we not have capacity? And what are, kind of those differences? So I guess before I get to that, I'm jumping ahead of slide, but I also want to, call out, so we do have 2 wastewater treatment plants, total combined capacity just shy of 30 treatment capacity. That's average day. Our lift stations, though, we have almost 400 million gallons per day of total pumping capacity for lift stations. So this massive system, right? And lots of capacities and lots of interconnected force mains and lift stations in series. And it just really kind of speaks to that extra complexity.
I don't understand. Say that again?
Yeah, so the treatment plant capacity up to almost 30 MGD, that's just, okay, on average, what we call annual average day. So typically, what is the capacity of the plant? We'll get into kind of the full projections in a minute. And that's just, how do we treat the water that the plants receive? But the lift stations, in order to get it there, when you add all the pumps that we have together, it's 10 times, more than 10 times the capacity. And again, it just kind of speaks to the complexity of the system. Like we talked about on the outskirts. So if you have, development or a neighborhood on the outskirts, they have a lift station that they are served by that then pumps into another lift station, that pumps into another lift station, then pumps to the plant, right? And so each step along the way is capacity that we have to provide and energy that we have to impart into the system to get it to the treatment plant just to provide service to those customers. That makes sense?
Does anybody have like different water rates depending on the cost to serve? Like the further they are from a water treatment plant?
Mhm. I can't answer that question for you guys specifically. I can tell you industry-wide, that's not fairly common. So typically it's within the city limits and outside, or maybe different usage types. But I got a, kind of another example of the schematic there, but again, we're just trying to kind of understand, okay, how does the system operate? So next, we did the same thing that we did on the water side, we did something similar to the wastewater side. We do what's called temporary flow monitoring. So we work with a contractor to install these flow monitors actually in the system, and that can observe not only what we call level surcharging, but also the flow rate in the system. So we had 20 temporary flow monitors that we put out for almost 90 days, I believe, to kind of record and observe, okay, how does the existing system operate? We used all that information and kind of all the data that we collected, on the GIS side with the SCADA, information on the lift stations, effluent data going back. I think we only were able to go back to 2014 on the wastewater plants. But trying to get all that data that we can to build our hydraulic model to kind of represent that existing collection system digitally. And then we calibrate that system. And we do a little bit of different calibration. We're looking at actually 2 periods. And so we do a dry weather calibration a week. Typical representative from day like today where it's not raining. What are the existing customer base? How are they contributing flow into the wastewater system? We're able to calibrate that to 0.5% error Industry average is 5%, so we're feeling pretty good about the model calibration that we achieved for dry weather. Our wastewater system, though, the primary capacity constraint is during peak wet weather events, is what we call it. When it rains, we have rainfall-derived inflow and infiltration that enters into the collection system. And, unfortunately, the systems aren't that tight. It leaks. Rainwater enters into that system, and we still have to treat it. We still have to have capacity for that increase in flow. We got to send it down to the plants. We still have to deal with it. And so that's the primary stressor for our wastewater system. So we also calibrate to wet weather events as well. I believe we had 3 wet weather calibration events. Not all of them, some of the meters would go out or, some various issues that wouldn't record good data, but across those events, we were able to get a really good calibration. It felt like that they were representative events for the peak flow that the system sees. And so we were able to get calibrated to the volume and the peak flow of 3%, about 2% error. Industry average there is 10. So, we again feel really good about the events that we saw and the calibrations that we were able to achieve on the wastewater system. Just because I skipped those points, so again, you guys have a lot of lift stations. The wastewater model requires a little bit extra information than the water model, so we're not quite able to model 100%. We were able to get 94% of the overall collection system, and that's pipelines. And of those 177, I believe, total lift stations, we're actively modeling 161 of them. So again, just a little extra information that we weren't able to find on some of those facilities. Industry average, I would say, is around 50%. So again, this is credit to y'all's staff and the data that we have available and working back and forth with them that we really feel like on both systems, we were able to get really representative models that, very as close as we can from a digital standpoint, a desktop standpoint, are able to match and represent both the distribution and collection systems. I think that's the end of our first one there. Before we go over into growth projections, any other questions on system operation and kind of that process there? So again, just kind of in summary, grab all the data that we can, put it into the, our models and try to come up with that representation as best we can. And then we start poking holes in things. Okay. Yeah, cool.
Quick question on the previous slide. The 391 million gallons per day. Is that you just multiply like 177 times?
No, so each facility, lift station has all these gravity infrastructure that goes to the lift station. There's typically a wet well. And then most lift stations have what's called submersible pumps. And so there's, pumps kind of submersed in the water. We have some different nomenclature, but it's anywhere from 2. So I think you'll have one with 5 pumps installed. Always at least 2 for redundancy, right? And so each of those pumps has a capacity. Again, kind of credit to staff and the information that they have that we're able to pull all of that. And I say approximately because, again, about 10 of them we just don't know. They're too old or too small. But we add all of that pumping capacity. So if every single pump in your system were to turn on at the same time, we'd have 391 million gallons flowing through that system at any given time. It doesn't really happen that way, but again, it's just provide context. Okay. That's a good question. Okay, so next piece. Okay, so that's our understanding of the existing system. Okay, now we dust off our crystal ball and try to think, okay, what's going to happen in the future? Fortunately, the city of Brownsville did some extra work with it kind of leading up to this project where they looked at what's called traffic survey zones, kind of county-wide to evaluate, okay, what are some potential growth areas, where are our existing customers, and where potential future development going to occur. So I got lots of numbers on here and lots of stuff in there, but ultimately we use that information to project out our future growth. The staff was able to provide us with, I think, 3 years of historical water billing data dating back to 2022, 23 and 24. So we were able to use that on the water customers, just typical billing stuff you guys get in the mail, pay your water bill. And that's what we use to kind of distribute our existing connection counts across both systems. The assumption there is that most customers that are water customers are going to also be wastewater customers. Like we talked about, that's not true in all cases. And so you see some minor differences, both currently existing and out into the future. But we took all that available information to us and kind of processed that down. We worked with staff to identify potential future developments, and then we phased them through what we're calling build out. Really, that's roughly 2050. Build out is kind of it's a moving target. You may have a commercial area that you think is built out, and then some developer goes and wants to put a skyscraper or something. That's just kind of the general process of how cities develop. So it's always changing, but we're trying to kind of peg, okay, what do we think that full development of the service area looks like? And we roughly anticipate that to occur around 2050, about 25 years from now. You kind of see all the numbers there. Overall, we're targeting a 1.5% growth rate. Historically, over the last 10 years, you're averaging right around there, sometimes a little high, sometimes a little low, but right around 1.5%. That's annually compounding. So, each year a little bit extra as you continue to grow. So that's kind of what we're anticipating to happen in the future. And we're going to take that and we'll get into that, but we'll take these future projections and apply them to our model. And that's how we start, trying to anticipate how is the system or the system going to perform in the future. So any questions on development, that future projection process? Okay. And I mentioned it there, but just to kind of show some additional information here. We work with staff, we work with the city to identify some potential developments that we had a little bit more information on. Okay, maybe they've been approved for a plat, maybe they've just submitted a plat, maybe they're in some sort of process. A fair amount of these are actually in construction right now. So things that we're aware of that are happening, making sure that we get them accounted for. So they're kind of shown on the map in the background in those kind of purple parcels. We're not drilling down quite to that level for everything. We're not going to say that every vacant parcel across the system develops. We're trying to get an idea of what we know and are aware of system-wide.
So you're thinking that these water and wastewater systems will grow by 50% over the next 25 years?
Yes, roughly. Yep, absolutely.
Okay.
Okay. Any other questions on that?
And this will be all really on the outskirts.
Yeah, I mean, you can kind of see that map in the background. I know it's hard to see from the scale. The vast majority of that, yeah, is kind of, there's some big development areas in the northwest, let me get my directions right. And then as well as kind of the southeast. And there's a little bit kind of interspersed. And, like I said, for some of these specific developments, we really drilled down in kind of the existing, city center. And we're looking at, okay, this is a, fairly large vacant parcel. How many units are we anticipating at that level? So there's a little bit of what we call infill development that occurs in kind of, the classical definition of the city of Brownsville. But yeah, most of that is focused on the outskirts for
So
sure.
new connections, what does that mean?
Yeah, that's a great question. That's conversations that we've had quite a bit going through this process. So it's intentionally kind of a vague term, right? So we're trying to kind of keep it what we would equate to a connection to the system, i.e. a meter that's installed. There's some kind of equivalency factors there. How do you differentiate between an apartment complex that just has one meter versus, another apartment complex where each unit is individually metered? So we're kind of doing some calculations on the back end to come up with those equivalents. And we're just kind of overarching saying that that's a simple connection. So you can kind of equate that. Is it three? I think it's 3 people per connection based on some of the other planning data. So if you want to kind of equate that to a population, it's roughly 3 people per connection.
I know. Are you going to go through maybe what that equates to in miles later?
Yeah, I don't have it broken up by miles, but yeah, we'll absolutely get to kind of our future recommended service extensions and that kind of stuff. Yeah, absolutely.
Okay.
Good. So now we're kind of equating, okay, that was just connections, right? Where is this new development going to occur? Now we kind of go back and say, okay, how does that impact the 2 systems? And we're converting that to water demand. What is our consumption? And then wastewater flow. What's that flow generation look like? And so there's some conversion factors you can kind of see there. And what's important here, I really want you guys to focus on the graph. So those colors are a little washed out on the screen here, but what's shown in what's supposed to be orange, the bar graph on the left, is all of that historical data that we were able to pull. It's simplified just to kind of what the average production was historically. And then those lines that we're projecting out into the future, that's our future projection on demand. And you'll notice that the historical production data, how much water have the treatment plants been producing every year on average, it stays relatively flat, a little bit up and down, kind of depending if it's dry or wet year, that kind of thing, relatively flat. As we actually dug into the data, on a per unit basis, that demand is actually decreasing slightly every year, about 1%. And what that means is that new developments come in, right? They're using, high efficiency washers or just maybe zero-scaping and just using less demand per unit every year. We hope that continues, right? Part of our task from a master planning standpoint, from a system-wide standpoint, is to not kind of account for, not rely on some of that conservation effect, right? And so, we were talking with staff about the difference between, water supply analysis versus the master plan and some of this other stuff. So if that trend were to continue, the average demand that we're projecting out in the future is that red line at the bottom. Stays relatively flat, grows a little bit. We're projecting a roughly 1.5% growth rate per year. So if you get 1% more efficient, that's really only 0.5% every year of increasing demand, right? So it stays pretty flat. We want to be conservative though. And so we looked at, okay, what is that per unit basis? How much water has been consumed historically? And that's where we come up with that 335 number. And that projecting out, if that holds true, it's constant, it doesn't decrease. That's that blue line that's shown there. And you see, again, like you said, about a 50% increase over the next 25 years. So we want to be on that conservative side for budgeting purposes, right? The hope is that we fall somewhere in the middle between that red and blue line, hopefully closer to red, right? But from a budgeting standpoint, we want to make sure that we're on the kind of high end of that equation so that we have appropriate capacities built in, we have appropriate contingencies built in. We're trying to move to this proactive management of the system. And so that's kind of what we're trying to account for moving forward. There's always kind of err on the high side, and then, okay, hopefully, we had a project that we were ready for and it's not needed. We're able to kind of track that information moving forward, and maybe we can push it off a year or two because of conservation efforts. So again, I think that's something important to kind of put into context that whether it's stuff that staff has been doing to plug leaks or repair lines or maintain efficiencies in their system, or even just your customers using less water and acting those water conservation methodologies, continuing to do that will be more efficient. We're able to save money that way. We don't want to rely on that it has to happen in order to manage our system. But if that continues to happen, that's will definitely bear fruits in the future as well if we can maintain that. Okay. So the last one I want to point out is ignoring the green line there at the top. So like we talked about, the primary kind of assessment of a water distribution system is done under maximum demand conditions. And that's really, okay, worst case scenario. So we define max day demand as your single largest day of the year where you use the most amount of water. Not showing any of that historical information, although we did process that and have that available. And so we come up with that peaking factor 1.5, and that's kind of applied to what that average demand is and scales that up. Where that green line intersects with that kind of lighter dashed line, that's where we roughly anticipate needing some extra treatment capacity, what we call production capacity. You're not in dire straits until it hits the top line, the top dashed line. That's your total production capacity, like I said, of 50 MGD. And we don't ever want to get there, right? We want to provide enough factor of safety. It's 80% of the total capacity is that first line. So roughly in that 2035 period, 2040 period is where we're anticipating needing some extra production capacity to provide enough kind of redundancy and factor of safety on this, again, kind of conservative demand estimate. So we'll be able to, staff will be able to track that. Every year we'll kind of go through, okay, what was our max day demand? What did it look like? Are we getting close to that, what I think is like 30 MGD? And as long as we're able to stay on top of that, we'll know we can track that in the future. We kind of continue to assess those growth rates and projections. But this is just to be conservative and kind of give us that initial target date of, okay, this is kind of roughly what we're thinking at some point in the next 10 to 15 years. Okay? We'll go into a little bit more specifics as we get into the further sections. But any questions on that water demand projection?
Does this take into account drought conditions?
Yes, and so that's exactly why we want to kind of err on that high end. And so what we did is, only had 10 years or I think it was again 13 years worth of data available to us, but we looked back over that 13 years, we're kind of incorporating those average conditions into there. So we're not necessarily planning for, the most extreme drought. We know there was definitely some drought conditions that occurred over the last decade, and those are kind of factored in. So yes, that's why we want to stay on that kind of blue line, that high side, so that we're on that conservative edge. Yes, sir. Okay. Wastewater side, it's got the same thing. We looked at the total effluent data from the wastewater treatment plants. We also, looked at all the historical data we had, consumption data on the water billing data, lift station SCADA, all of those sorts of things. Your average wastewater flow production per connection is 235. So generally, if you're watering your plants or something using, sprinkler system, that's water that shows up on the consumption side. It's water that the system has to produce and convey. It doesn't impact the wastewater system, right? So generally, your wastewater production number is less And the rule of thumb is 80%. You guys are less than that. And again, that kind of shows to, okay, like we're being efficient with our water use. We're being efficient with our wastewater production. And again, that's going to kind of pay dividends in the future. We did kind of a similar analysis. I'm not actually showing these graphs just so we can see those breakpoints a little bit better in the bar graph. The wastewater system is falling not anywhere near as significantly as the water system. It comes out to, it was like 0.2 or 0.3% negative rate per connection or flow per connection year over year. So similar kind of thing, less flexibility in terms of water conservation. And again, we're just showing the high side numbers, that historical average. What's important context here, though, is like I said earlier, the wastewater system is more sensitive to wet weather events. Climate change or what have you, as we have, big hurricanes or big storms that come in, those are going to negatively impact the wastewater system and the capacity that we have to be able to provide moving forward. So we want to make sure that we're on the conservative edge there. We're able to, we have some big 500-year event. We're not going to be able to account for that, but we still want to be on that conservative edge and on an average standpoint and make sure we're providing that capacity. So if we're not there, that just means that we're over prepared and can push projects out a year or two. Just to kind of give you a breakdown of the dashed lines, TCEQ does have what they call a 75-90% rule. So on the wastewater side, when you hit 75% of your wastewater treatment plant capacity, you have to start planning for an expansion. At 90%, you have to start constructing that expansion. The hope then, right, is never getting to that 100%. So those are what the dashed lines are shown there. And so again, roughly that same time period, roughly 2030, a little bit earlier, we're anticipating hitting that 75%. We need to start planning for some expansion. We're not quite anticipating to ever hit that 90%. And so there is kind of a wrinkle in that rule because we're projecting to build out, again, it's a moving target. We don't actually need to implement that expansion. So we'll talk a little bit later, kind of towards the end of the presentation about what do those alternatives look like? What are the kind of options that we have? So not quite needing that full expansion, but we're getting close and want to make sure that we have that accounted for as well. Any questions on wastewater? Yeah, Mike? Okay, so here's where the rubber meets the road. We're actually getting into design analysis. Okay, how are we actually identifying projects? How are the current systems performing? In regards to on the water system, we have a little bit more specific regulatory requirements. On the wastewater system, we have to use some best practices and things that we'll get into in a second. So TCEQ outlines in the Texas Administrative Code, Chapter 290, requirements that water systems have to be able to meet at a minimum. However, there is this kind of alternative, what we call alternative capacity requirement, ACR, for systems that are efficient with their water use. You can apply for this ACR, and it gives you some a little extra flexibility in terms of how these requirements or how we assess these requirements. So BPB does have an ACR, and it's at that 68%, which basically just applies as a straight reduction across all of these assessment criteria. Okay, so again, compliments to staff, compliments to how customers and how the systems have been managed in the past, that we're able to be efficient with these usage and how we're have used our water distribution system, that we don't have to meet these most stringent requirements moving forward. So we definitely want to make sure that we're leveraging that ACR and able to maintain that in the future. So we'll kind of get into it, and here's all of the existing system checks. But again, in general, because of that ACR and because of how efficient the system has been, we're meeting all of the requirements that we need to meet right now. We are in compliance and doing what we need to do. We want to make sure that we continue to do that moving forward. So we evaluate production capacity, like we talked about. It's also elevated storage and total storage, and then distribution pumping as well. And so that's being able to meet peak demands and that kind of thing throughout the system. Okay, so we'll get into the specifics of each of those tables and the actual numbers. But the takeaway here is that your existing water system is in good shape. Yeah. Questions there? All right. So I got a couple graphs, and this is what you were talking about earlier, that spatial component. So the first one here is fire flow. The requirements vary by development type, and even different cities and things have different requirements. So this is just kind of to provide some context for how well the capacity of the system is. Anything that's yellow or better, we consider good. So you see there's a little bit of pockets of orange in areas where, okay, we're anticipating not having the best capacity. It's not necessarily required in those systems. But trying to kind of evaluate that, okay, where do we have capacity deficiencies? How can we improve those in the future? The primary limiting factor for a fire flow is just having appropriate, I apologize. Yeah, so It's the maximum sustained flow rate that the distribution system can handle. So it's called fire flow because it's, during, emergency event, the fire event. If the fire department kind of hooks up to a hydrant and they're wanting to pull as much water as they can, this is an approximation of how much water they can pull out from that. So 1,500 is that kind of rule of thumb. Anything greater than that is good. Again, some developments, a big industrial customer may need higher requirements. And anything lower than that's not necessarily bad, but definitely something we want to be aware of and try to fix in the future. The primary restriction for fire flow is looping. You have multiple ways for the water to get there. That usually gets you enough of the capacity that you need. So a lot of these areas in orange, it's just because there's only one supply line. As long as we can bring in that second supply line, and we've got some examples of that, these values get a lot better in the future. So we'll kind of continue looking towards that. And then like we talked about earlier, pressure. So again, this is the one that the TCQ really evaluates. We have to be able to, on a max day standpoint, on a peak hour demand, any given hour in the year, have to maintain 35 PSI across the system. So anything that would show up in red on this is bad, it's not good. We've got to be able to solve that. This is the worst case scenario. It's the single highest demand hour throughout any given year. So it doesn't happen very often, but we still, want to stress the system to that level. And as you guys see, doing great. I think the minimum existing pressure in the system is right at 40 PSI, which is kind of what we would recommend, above that threshold. So system's in good shape. We just want to, continue to make sure we can do that moving forward. Go ahead.
Are there any red? I don't see any red.
No, if they do, and I don't think we took them out. So on your treatment plants, we have a node in the model that models the suction side of the pumps. And those are just based at atmosphere pressure. So they're like at 10 PSI. But because you're not actually serving the customer, those don't actually count. So you see a red if you can see really closely on there, that's likely what those are. But like I said, minimum distribution service connection pressure is about 40 PSI.
Yeah, I see a couple of orange, but
Yeah. And again, that's that kind of like, okay, like orange is maybe not like still meeting the requirement, but that's getting a little bit close to comfort, right? And so we want to make sure that we can enhance those pressures moving forward in the future. So this is just minimum pressure. So anybody out there that's looking for their house or something like that, this is the single lowest pressure hour in any given year. So you probably won't notice pressures be gone. Okay. All right, so that's the existing system. Now we take that, we apply our growth projections, right? And how does the system perform moving forward into the future? So again, I'm not going to dive into all of these specifics here, but you'll see, okay, that we've got a couple of checks. There's some no's in that table, right? That out in 2035, out in 2045, we're anticipating, wait a second, we're going to need some extra capacity. So the first one is there at production, like we said, roughly when we hit that 80% line in our demand, we're going to need some extra production capacity. Staff is working on, okay, where's our plan? We have some plans in place to be able to get that information. And really all we're looking at here is the timing. Okay, from a budgeting standpoint, when can we start accounting for these? We're going to need these projects. We want to make sure we got plenty of heads up on that, right? We don't want to get too close to those requirements. And then, oh no, it happens faster than we thought, and we don't have the answers. So roughly in that 2045, we're going to need some extra production capacity. If I remember the numbers correctly, yeah, we're looking at like a 10% increase through 2050. So it's like just barely over the production capacity that we're able to provide to make sure that we can do that. Again, that's a little bit different from water supply. It is related. This is just how can we get treated water into the system. So the water supply, and I know you guys have a drought contingency plan and some other studies going on. Those are related to this, but not quite the same. So a little bit different. Distribution pumping's good. We're covered there. We are going to need, from a redundancy standpoint, so that's where that alternative pumping requirement comes in. There's some extra kind of, different rules that are applied and things. And when you only account for any facilities that just have one pump available, that's fine. It can count towards the strictest definition of the requirement, but we also want to make sure we have enough redundancy. And obviously you have one pump, if it fails, needs some work or something, there's no redundancy there. So we are showing in 2050, we're going to need a little bit extra redundancy just to cover us. But, overall pumping is good. Next slide here is storage. Generally, we're looking pretty good here. We're just barely breaking that elevated storage requirement in 2050. You guys actually do have 7 million gallons of elevated storage available right now. One of those ESTs is going to be decommissioned for condition related. So if at some point over the next 20 years, maybe we want to put another one back, something like that to get us over that requirement, but just barely kind of tipping over that requirement there. Okay, so any questions or future water system analysis?
So in the previous slide, okay, so in the top table, the total available production capacity at 34.7.
That's correct.
So we compare that to which other column?
Yeah, that's a great question. So yeah, lots of numbers on here, but it's all the things that we're checking. That alternative production capacity requirement, what is the fourth column from the left? That's what we're checking. So the fourth column and the second to last column, that's what we're comparing. So you see that 34,722, and how does that compare to, what is that, 38,558, 8.6? Just barely over 15%, 10%, something like that.
And why not that minimum required production?
That's your ACR, right? So that's that alternative capacity requirement. It's based on how historically how efficient your system is being. We want to make sure that we can, continue to be that efficient and that applies in the future. We'll definitely stay on top of that. But that's for reference. That's what every other system in the state is assessed on.
The alternative one?
Yep. And I didn't mention, I think I forgot earlier. Let me go back to the slides for you. You see that table on the top left? We talked about that 335 of your average consumption per connection, but that max day peaking factor and peak hour peaking factor of 1.5 each. Typical rules of thumb there are 2. So again, you guys are can't go less than 1. So you guys are in a really good spot there with how the system has been maintained and operated, and even again, how your customers have been using water historically. And we continue to do that, continue to kind of leverage those things from a capacity standpoint. That ACR is where that comes out regulatory, or how it applies to the regulatory requirements. So as long as we're able to kind of keep that moving forward, we'll be able to stay on top of that. And this is the table that shows that ACR requirement, 68%. Okay.
So maybe you explain it to me another way. So
Sure.
why do we ignore the minimum required production?
Yeah, because BPUB has gone through with TCQ, the alternative capacity requirement. We have that active. So TCQ has those requirements for a typical system, because you guys are typical, right? Like your system's in good shape, it's very efficient. And this ACR is how we change the regulatory requirements. And TCQ has approved that to apply
like a
moving
waiver.
forward. Yeah, exactly. It's a waiver. Yeah,
Okay.
exactly. Okay, anything else on water? Okay, wastewater next. So unfortunately, the water requirements are very prescriptive. We got to meet, all of these different requirements. We don't have that same thing on the wastewater side. There's a little bit, but for the most part, it's just don't have sanitary sewer overflows. Don't spill wastewater out of the system. How we do that, we kind of take a look at some other, sources, industry standards, and just rules of thumb that we come up with based on our experience. I'm not going to go into detail on all those tables, but this is the design criteria that we've assessed the wastewater system on. Oh, sorry. Thank you. Okay, the big one I want to point out is this design storm. So we utilize NOAA Atlas 14, so it's called, that's the National Oceanic Atmospheric Administration. There we go. They do a ton of work. It's really cool stuff if you're interested in this kind of thing. But they go back, I think it's like 300 storm events historically, evaluate it locally. What are the most common storm events that are observed in the area? And we come up with what we call a design storm. So this is a synthetic event. It's fake. It's not real. But how we assess that system, the wastewater system moving forward, like we talked about. Most wastewater systems are most sensitive to wet weather events. So we want to come up with a representative wet weather event to assess the system. And what we came up with is this 5-year, 24-hour storm event. The 5-year is basically how significant that storm is. Doesn't quite work this way, but it's roughly, you can expect the storm to occur once every 5 years, right? It's called the 20% annual probability of exceedance. And this is kind of what that shape is. And so the duration and what's called the Haida graph, how it changes over time, that's based on historical events. So what Brownsville and kind of the Valley area in general is most sensitive to, right, are these big sustained storm events. You're not like North Texas, you're not getting these huge thunderstorms that are really high intensity and short duration, but it's these kind of long events that bring a lot of volume, maybe not high intensity. Those are just kind of what that representative storm looks like, okay? So we apply that to the existing system to assess collection system capacity, okay? Like we talked about,
what?
Assess collection system capacity. So what is the capacity of your wastewater system? When that storm event hits, when customers are using, flushing their toilets, all that kind of thing, on top of that storm coming in, and we have RDII, we have rainfall entering into the system, what is the system's capacity to convey that flow through the system without spilling? Okay. I want to kind of stress, this is, desktop analysis. This is a synthetic storm. It's not real. This is how we're assessing that system. And we want to be, stringent on how we provide that assessment. Okay. So of the 177 or 160 lift stations that we have actively in the model, we're showing 50 of them to be greater than have actually experienced peak flows greater than what's called the firm capacity. And then another 16 that are greater than the total capacity. The total capacity is, you got 2 pumps, all the pumps that are in that lift station turned on. Firm capacity is where we assess redundancy. So again, if the pump goes out, you lose power, something like that, it's in the shop for maintenance. We always only have 1 extra pump in the system to have some redundancy. So ultimately, our design criteria is assessed on providing firm capacity to convey peak flows. Okay, so if you add those two together, that's 66 out of the 170, right? So we're about 40% of the system is showing issues under this kind of worst case scenario event, right? That's kind of how we establish those criteria. We want to elevate those facilities. We want to do some expansions to provide enough capacity to convey that flow. Okay. What's shown on the map here, those kind of, it's yellow and there's some red dots and blue and red lines. Those are what we're projecting as capacity restrictions. And those are candidates for capacity expansion moving forward. Okay. So again, really complex system. The wastewater system is really complex. That means that there's a lot of inner workings here that you kind of see, like some areas will have an issue that then gets kicked down to another lift station that, and so it's all interconnected. And we want to make sure all the ways, all the steps down through the process, we have enough capacity to convey that peak flow. Ultimately, what we're trying to avoid is spilling any of that wastewater during the peak event. And that's our goal. Okay.
So how come we don't see the green one here?
What do you mean by green?
Like the ones that are working? The ones that are working well?
Oh, yeah, because, I mean, so, of the, if there's 66 that we're identifying for expansion, the other ones aren't, right? No, that doesn't mean that they're not in there. But we're just, we're focused on the ones that we want to expand.
So what does surcharge do to downstream restriction mean?
Yeah, so that typically when you see that, that means that one of those lift stations is struggling to keep up with the peak flow. And what happens is you think of it like a bathtub, right? If the drain of your bathtub is plugged and that faucet's on, it just keeps rising and rising and rising. That's surcharging in the system, and the wastewater system works the same way. So if the lift station is struggling to pump that peak flow through, the system continues to rise and rise and rise until it hits the manhole, the top of the manhole lid, and spills out. And that's an SSO, sanitary sewer overflow. So these are projected, predicted, they're not real. Again, just what we're kind of projecting under this design storm event. Under this.
These are not happening right now.
Exactly. Yeah, exactly. So we did kind of work with historical locations and work with operations staff to kind of go through, okay, we're showing this lift station to be an issue. How does that track with how you guys have been maintaining the system? What you see when it rains, a lot of your operators go out during storm events and make sure that these lift stations are operating, they're still running, that lightning didn't kill the power, that kind of thing. And so they know where all these issues are. And we did kind of work through with them to say, hey, we're showing an issue here. Does that track with what you're seeing? And in general, we're in agreement there. So our goal here is to be able to withstand an event like this.
So they are real. I guess.
Well, they correlate, right? But, this 5-year event it's a synthetic event based on historical averages. So you may never get one. You may get one much bigger than that, right? A big hurricane or something comes through. So it's just our assessment criteria. So it correlates with what ops staff have seen historically. But yeah, I mean, you're never going to get this exact result. So I want to kind of put that grain of sand on it.
But are the ones that staff gets reports from included here?
No, we're not showing historical SSOs here. These are just predicted.
So there might be more red one if we were to include reports from customers.
Yeah, I don't know what the counts are there, but yeah, I mean, any wastewater system is going to have overflows. Whether that's a peak event, lack of capacity, or even just some sort of like failure, if a lift station fails or loses power, right? Something like that. So, yeah, we want to take that with a grain of salt, right? We want to kind of look at it and kind of gut check with historical events, but also kind of be predictive and forward thinking with how we're assessing the system. So again, the big takeaway here is, the water system's looking pretty good. With how we're assessing the wastewater system, about 40% of it is going to need some amount of expansion improvement, in the, either now or in the future, right? And there's kind of varying levels of that. We'll get into that as we get into the CIP, the priority of what those improvements are. Okay.
And just for my understanding, is it due to the rainwater going in more in the ones that are red? Or is it due to, what?
Yeah, a lack of capacity in the system would be the other option. But yeah, that's a very good question. So part of the reason we do those temporary flow monitors is you're going to have what's called different RDII rates. That's again, rainfall derived influent infiltration is a fancy way of saying how the rainwater enters into the system. And that's going to vary spatially across the system. So we had 20 of those monitors put out where we get an idea of, okay, in this area, this has high INI. This area over here has low INI. It's a buttoned up system, doesn't have a lot of leaks. So absolutely that will vary moving kind of across the system. Our assumptions are that, we vary that kind of spatially based on our observed data and that those are held constant through the future. So typically what we find is, your staff's going to work, to try to button those things up. We're going to replace lines. We're going to rehab infrastructure to try to button that up. But as systems age, right, they get leakier. And so, we're not saying that your INI rates are going to increase, but we're also not saying that we're going to be able to substantially decrease those rates either. So what I can say is that you guys are right, kind of in range of what we would expect to see. So we didn't observe anything that's like, oh, that's a big issue that we need to address. So yeah, absolutely that varies spatially. For the most part, though, it's the other issue. It's just lack of capacity. We need some extra pumps or bigger pumps.
Extra pumps? Thank you.
Yeah, it's a good question. Thank you. Okay. So again, there's a bunch of numbers on here. You guys have 177 lift stations, so they're not actually all shown on this table. But again, just trying to show you, okay, so what we do is we use our model, we use our growth projection, and for every single facility, we're looking at, okay, what's the capacity, both total and firm. Again, that firm is kind of redundancy sake. And then even the force main has a capacity as well that we're assessing. And then projecting that both existing in 22 and 2025, and then all the way out through 2050. So lots of numbers on here. And what's important is as they change, right, as new development occurs, or maybe, we have some projects to reroute force mains to some other areas in the system, those flows are going to change. And so when we're expanding facilities, we want to make sure that we have enough capacity, both for flows today and what we're anticipating out into the future. So this is just an example of kind of how we perform that analysis on every facility throughout the collection system, but also through all of our future planning phases.
Okay. And you're prioritizing.
Exactly. Yep. Exactly. Yeah. We'll get to that in just a second. Okay. So here's the big one. Okay. So up until this point, all of the work has been, okay, how do we get here? Are we assessing the system? Are we representing the existing systems well? What are we predicting out into the future? Here's our CIP, right? So we've identified all these problems. How do we fix them? Okay. So there's lots of stuff on here, and I know it's hard to see on the map. We're going to get to the next slide. I'm trying to preface this a little bit so you don't get shocked too much by the numbers that we're showing here, okay?
Yeah.
So we have projects.
I want to know how much it is going to cost.
I know. We have projects that were recommended, just to show you on the map here. Red is 5-year, blue is 10-year, green is 20, and then purple's build out. So again, roughly 25-year, but that's flexible. These things are prioritized, and what we worked with staff to kind of narrow down is what is the projects that we need that are highest priority to continue maintaining the level of service that we're able to provide as kind of a system-wide growth occurs, kind of just focused on that 1.5% annual growth rate, that kind of thing. Alleviating existing restrictions that we see, but for the most part, just enhancing that existing level of service and maintaining that. Anything that's outside of those red projects, those start to be more focused for specific developments. So like we talked about, there's some of this stuff kind of in that Olmedo area, the northwest of the system, that is going to, lots of development that's going to occur, get down even in the southwest as well. And then in the southeast are these like big kind of development areas. You'll notice a higher density of projects in those areas, but for the most part, those are phased out because we're calling them what's called development driven or kind of, future to serve anticipated growth. Okay.
So the purple is new stuff.
No, so anything that's shown kind of in the red, blue, green, or purple is projects that were recommended. Anything that's in purple, though, is low priority. Red is high priority, and then, blue is slightly less, green is slightly less. Okay? All right, here's a big one. It washes out. I apologize for that. So what we do is we, evaluate all these projects, pipelines, pump station extensions, tanks, that kind of thing, come up with cost estimates, okay? Those cost estimates are based on historical projects, things you guys are working on right now, other, projects and other utilities in the area. And again, we want this to be conservative. This is for budgeting purposes. So our goal here is that if we say, okay, a project's going to be 5 million, maybe it comes in at 4, maybe it's 4.5. That's great. We don't want it to come in at 6, right? And so we're trying to be on that high side to make sure for budgeting purposes that we have enough funding available. These again are prioritized. So anything that's shown in the 5-year is, identifying some of those limited kind of existing system deficiencies on the water side that we identified, but also again, just continuing to enhance capacity as system-wide things grow into the future. What's shown in red, we're, budgeting roughly to be implemented in the 5-year period. Blue is 10 years, green is 20. And purple is just, kind of for future growth out into the future. So you can kind of see over the 5-year period, we got 32 million. And then again, between 5 and 10 years, that increases to about 50 million. That number, the total numbers are really big. But if you'll notice, you kind of dig into it, that line item 20 at the bottom of the green, that's our treatment plant expansion. So we're anticipating and have worked with staff to kind of identify expansion to SRWA's brackish groundwater treatment plant. And unfortunately, these treatment plant projects are just really expensive. So we think we're going to need that. We're kind of anticipating that into the future. But that's the single largest line item there, more than half of the total cost. So how do we feel about that? Questions? You haven't jaw's not on the floor. You haven't left yet. So how do we feel about that?
I think it's pretty straightforward, right? So 5 years more realistic. The rest is kind of projecting. So yeah, I mean, we know that there's investment that's needed, and I think this is just part of the process in identifying, just how much so that we can be prepared. Looking at budgets and plans and CIP projects and so on.
So, and that's exactly what we want. That's exactly what we're going to do. This is a budgeting tool moving forward, trying to be proactive in the management of the system, right? So we're trying to, empower you guys and empower staff to have these tools available to know, okay, what are the projects that we need? How much are they going to cost? When do we need them? What's the best alternative to kind of solve the problems that we're dealing with? So it's a plan, right? That's kind of the whole point here. So, yeah, obviously we want those numbers to be as small as possible. But, we all know COVID and, construction costs and all sorts of things going on that we've kind of seen these numbers increase over time. And we just want to try to stay ahead of the curve. That's all we're trying to do.
Sure.
So give you
Other than cost, is there any value in maybe adding columns that would indicate either flow capacity or storage capacity or just treatment capacity?
Yeah, absolutely. Yeah, we could definitely add some additional information. What I will say, obviously this is a presentation format. We're going to have a draft report available or, final report here shortly. And each of these projects has a 1-pager, kind of what we call a cost sheet that details, okay, this is what the project is. Here's the extents. Here's what it is. If it's a new tank, what's the size, what's the location, that kind of thing. And then even breaks that down into individual line items. So, okay, a 12-inch line costs this much, a 24-inch line is this much, that kind of thing. So this is just the overall summary for, our purposes here, high level. The last thing I want to say on this, and we'll get to that kind of here at the end, what's next, right? We're also going to start looking at impact fees. So a lot of this stuff is, driven by future growth. And here in Texas, we do have impact fees as available funding mechanism to help kind of recoup some of that cost and provide funding. You do, that's right. We're required to update them every 5 years, and you guys are due, right? So that's as soon as we're done with this master plan and have all this stuff finalized, we're going to get going on the impact fees and go through that update as well. So all of this information in here, both the capital plan, the projects that we're anticipating, and the future growth that we're anticipating over the next, impact fees are on a 10-year period. We'll kind of incorporate that and update your fees to kind of be in line with all of that, so that as much as we can, and however those conversations go moving forward, that we have that as an available alternative for funding.
impact fees, change over time, right? I guess that's why we have to do it every 5 years.
Yeah, you're
Well,
required to update every 5
Yeah.
years.
Normally, does it go up?
Yeah, generally, as systems grow, right, the more growth you have to have more projects to sustain that growth. So impact fees are a simple calculation of how much money are you spending on capital projects divided by how much growth you're anticipated per unit. That's your fee per unit, right? And it's a little more complicated than that, but high level. So if you grow more, you got more projects. So generally, it's kind of 1-to-1. The primary change that we see is, like I said, is just construction cost changes. And we know, so they've flattened over the last couple of years, but especially 2020, 21, things nearly almost doubled. In some cases, more than doubled. So that's going to be the big change. You remember, Marie, is it 2017 or 2019 was a previous study?
The last one,
Mhm.
2015.
That's right.
But the reports that are done on impact fees come up with recommendations. Ultimately, it's the city commission that adopts. Particularly in our last one, the recommendation were higher. They adopted lower fees. So
Okay.
it's up to them.
Yeah, absolutely. The sole discretion is kind of left to city council, right? So, again, this is just an option to us, and we want to make sure that the option that we have available is up to date with our current plan. How they, kind of choose to subsidize development, so to speak, is, ultimately up to them. But
Okay, so when we make a recommendation, let's assume that we're making it aligned to, these estimates. If they were to adopt a higher impact fee, would that mean that we would be better prepared for this scenario? And if it's lower, we're less prepared?
no, so, your capital improvement plan and the projects that we have to implement are relatively independent. It's just how do we continue to kind of maintain our service? And so generally, the give and a take is that funding coming from development and from new customers? Or is it, assessed on the existing customers and future customers through increased rates? And so again, that's kind of where that break-even point occurs. Impact fees are not, it's not like a grant or a loan and we're able to get, funding for a project. It's really a way to recoup costs that we're already spending on, capacity enhancements in the future.
Okay.
So yeah, it's a give and a take between rates and trying to find that balance between, we want to, encourage development to occur, but we also want them to pay their fair share. And so what's that balance between new customers and what they pay versus existing customers to rate?
Okay.
So yeah, not quite what we're talking about today, but again, in kind of the same vein. So it's worth talking about. So that's water. Okay. Now we go to wastewater. Again, kind of zoomed out here. It's kind of hard to see, but same general process here. So we prioritize projects in the 5-year window. Anything in red is kind of that high priority. And then we kind of phased out. So blue is 10-year, green is 20, purple is kind of that long-term build out, 25 years. So what we did is that we kind of changed our assessment to say, okay, we want to be able to provide firm capacity for all your lift stations. You got so many lift stations, you're primarily a lift station driven system. So how we assess and plan for those lift stations kind of changes for the wastewater system moving forward. So we're going to be able to plan for firm capacity, but we know that we've got total capacity. We have that extra pump. So in a worst case scenario, we can't account for that. So we've adjusted our phasing to say, okay, any facility that experiences peak flows greater than firm capacity, but it's less than total capacity, those are going to be a lower priority than something that doesn't even have total capacity to keep up, right? Or even if they have total, they don't quite have total capacity, if there's enough storage available in the system to not cause a projected SSO, right? Then, we can kind of attenuate that peak flow and store it in the bathtub, so to speak. Then those are even, lower priority than those ones that, we are anticipating don't have enough storage, don't have enough pumping capacity. So we've kind of been able to broaden our assessment criteria and prioritize accordingly, where we're only focusing on the most important aspects of the system, the highest, the most critical capacity restrictions. Okay, and those are our highest priority projects.
Question.
Mhm.
Like when the Texas Water Development Board prioritizes project for funding, they use, for example, like the number of people that are affected.
Yeah, absolutely.
Also, property, value property or things like that.
Mhm.
But here, when you prioritize, you're mostly focused, if I'm understanding correctly, on the capacity of
Correct.
the system, regardless of how many people.
Well, so they are, especially within the phases, they are also prioritized. So a lift station that serves, a quarter of the system is going to be a higher priority than a lift station only serves one neighborhood, right? So we're not looking at it quite the same way the Texas Water Development Board is. I know there's some other factors that they incorporate as well. But yeah, it is similar in that we're trying to say, okay, this is your most critical project. And we'll kind of get into that on the next slide there, that there's a couple of projects that's like, hey, we know where these major problems are, and here's how we're kind of stepping through the process to solve those kind of one at a time.
Okay.
Okay. So this is the big one. So here's kind of all those numbers there. So again, your wastewater system is far more complex than your water system, one of the most complex in the state. And that comes out in that how we are able to maintain that moving forward, expand that capacity, make sure that we're able to kind of keep up with that system and that complexity. Unfortunately comes out in kind of higher cost estimates. So we're in that 70 million range, kind of within that 5 years, roughly double. That tape starts to taper down a little bit in terms of the comparison for future years. And then even within each of these phases, exactly like we're talking about, there's some adjustments that we make to priority. So that, project number one is kind of that there's a force main along Alton Glore that is a primary restriction that, gosh, there's a dozen or so lift stations that utilize this one force main. And so having that, adequate capacity there resolves a lot of issues for that whole kind of northwestern area of the system. It's not shown here. It is shown on the map, although it's hard to see. But you're currently working on what we call the North Regional Force Main. Let me actually point it out. It's that orange line at the very top of the map there. That's your number one issue. And you guys are already working on that, already aware of that. It's funny, as we're having conversations about system capacity, with staff, Marie was like, wait a second, like this project you're showing right here, we're already working on that one, when we were kind of going through that initial draft. So it's really good kind of a gut check for us that we're on the right page, but also a good kind of validation for staff that they're aware of these issues and working towards them and, kind of staying on top of things. So the primary, number one problem, we've already got a solution and it's under construction, is that right? It's fixing to go, about to go. Yeah. So about to go to construction, right? So already kind of on top of that. So we've got that problem solved. Now we're going on to the next one, right? One step at a time. Okay. I think that's kind of the majority to talk about on the wastewater system. Again, it's such a complex system. There's lots of rerouting force mains and trying to find available capacity. And, this one lift station doesn't have capacity, but if we pull this lift station off of it and send it elsewhere, there is enough capacity. So lots of changes and, it's going to be a, process. But what we're trying to lay out here is a plan moving forward. We can say, okay, this project's going to solve this problem and have enough capacity, for the next 25 years, and then move on to the next one. So, trying to outline that plan and that implementation strategy and prioritize accordingly. Okay. Go ahead. You have a question?
No, thank you.
So last slide we got here, we talked about treatment plant capacity. Again, we're not really anticipating that you need that, but we want to make sure we have a plan in place. And so we've kind of identified, I apologize, the roads have kind of washed out. But this is in that northwest area of the system. It's right north of the sports park, the new sports park. So kind of right in between the two highways, 69 East and where that toll is like 169, right? 550 State Highway.
What neighborhood is that you can see on the top?
Oh, I couldn't tell you. I'm sorry. But yeah, we're right kind of on the northwestern side of the system. Which neighborhood is that on the top left?
Zoned by the animal shelter?
Ah, okay.
It's I believe it's north of the railroad for.
No. And BPUB actually owns land in this area, and that was one of the reasons we kind of identified this. This is currently industrial. There's nothing there, So, whether or not this is actually the location, but we want to kind of come up with a plan. If we need this capacity in the future, there's something that it could start to look like, start looking at, budget standpoint, and also the hydraulic capacity standpoint. So you can see it a little bit better, that orange force main that kind of zigs through the sports park and kind of down Paredes Line Road is what that is. It took a second. But that's that North Regional Force Main. And this works great if we, move down this way, that you can just kind of pick any location on that force main, we'll divert flow off of that. It can kind of divert this entire northwestern quarter to third of the system into this new plant, whatever it is, we feel like we need to implement that, if the case, maybe. So we had that in there, budgeted again. We don't think we need it. It's not incorporated in the other CIP, but we have that as an option should it come up in the future. Okay. So that's what we got there. What's next? Path forward. So like we talked about, we're wrapping this stuff up. We're going to present to the board here early next month at the next board meeting. And then we're going to get going with the impact fees and, have kind of that available funding mechanism should we choose to use it, or how we implement that. It will be available to us if we get going on that. Okay. So thank you for your time. I'm not wearing my watch today, so I have no idea how I did on time, but I do very much appreciate the opportunity. Any other questions or anything?
Thank you. No, it's great.
Yeah, very informative. Thank you. And yeah, we'll wait to see if there's any other questions from the rest of the board.
Yeah, absolutely. Absolutely. Great. Well, thank you so much.
Thank you. Now we just have one more item. Any requests for future agenda item? I don't have any at this moment. No?
I was gonna joke and say that we need more details, but no, we need less details probably. But thank you for that. No additional items.
Okay, so then we are ready to adjourn. Thank you all for being here and hope you have a great day.